All right, welcome back. We're going to continue with our measure theory review before we start talking about complex analysis. Again, just to look ahead, once we finish this measure theory review, I want to talk a little bit about some complex analysis. We'll cover some basics of holomorphic functions and all that business. It'll probably take about 4 videos. As far as the time frame for when we start actually talking about the first subject of functional analysis, normed linear spaces, let me actually just pull up my notes here. Right now, so in this video, we're going to be covering some properties of measures. After this, we'll be discussing the Lebesgue measure. That'll probably take a couple videos. Then we're going to discuss Lebesgue integration. That might just be one video, or I might split that one into 2. So we're at 4 videos so far, and then I want to talk about some 2 very big theorems in measure theory, monotone and dominated convergence. So you're looking at about 6 to 7 short videos, so hopefully not too much longer with this review. And then complex analysis, it'll be a lot shorter of a review, maybe 4 videos, hopefully at most. Okay, so we've got a little bit of ways to go, but continuing nonetheless with our measure theory review. Today is a very basic video. We're just going to be talking about a particular list of properties of working in measure spaces. Before I start discussing that, though, I want to introduce some new terminology. So when working in a measure space, and you recall what that is, that's a triplet. We've got a set X, we've got a sigma algebra over that set, and then we've got a measure over that sigma algebra. Okay. The terminology, the new terminology is that we refer to elements of that sigma algebra in our measure space as mu measurable sets, or we can just refer to them as measurable sets if we know what the measure is. Okay, so anytime, so instead of saying let A be an element of a sigma algebra, I'll just say let A be a measurable set. Okay, very basic. So, just this video is very simple. I want to cover 4 basic and very, just quite fundamentally useful properties of measure spaces. The first 2 properties here, right here, 1 and 2, I'll just write a note here. These work for any sigma algebra. Meaning the first 2 properties are actually just properties of sigma algebras. You don't need a measure or anything to prove them. Okay. But this is just, today will be kind of a nice practice of what we've learned so far. You can see all these properties of measure spaces being used in these proofs. So the first property is that the finite union of any measurable sets is measurable. Now you recall the definition of a sigma algebra. It's closed under countable unions. Okay, so we're dropping down and saying because it's closed under countable unions, it's also closed under finite unions. Okay, so this property number 1, you can just say it's the property that states the closure of sigma algebras under finite union. Property 2 is that a finite or countable intersection of measurable sets is measurable. In particular, sigma algebras are closed under finite or countable intersections. So you can also take intersections and stay in your sigma algebra. This one's quite nice. A couple things come from it. One is that you'll get that sigma algebras are closed under set subtraction. So you can take a lot of set operations and stay inside your sigma algebra. But again, I'm just switching that sigma algebra terminology out and using measurable sets instead. Means the same thing, but this is just quicker to say. And then our third property is quite intuitive. The measure of the empty set is 0 in any measure space. So you can never have like the measure of the empty set is something that's non-zero. It'll always be 0. And then the last property we'll prove today is that if A and B are measurable sets and A is a subset of B, then the measure of A is less than the measure of B, less than or equal to the measure of B. And this is quite intuitive, right? If I have the bigger the set, the bigger the value of the measure should be. Or at least it should stay equal, right? I should never have a bigger set and the value of the measure decreases. Okay, so these are all some very intuitive properties, and they're quite easy to prove. We'll start with the first one. I'll just copy this here. So let's prove that the finite union of measurable sets is measurable. And like I said, we already know that for a sigma algebra, maybe I'll write this proof in green, we already know sigma algebras are closed under countable unions. under countable unions. Okay, so how are we going to prove this? Well, we want to prove that given a finite collection of measurable sets, in particular, again, I'll just keep repeating it so you remember it. That means the finite union of elements of my sigma algebra. How can I write that as a countable union? Because if I can write a finite union as a countable union, I can exploit the fact we know that countable union will be an element of the sigma algebra. So therefore that finite union will be an element of the sigma algebra. This is quite simple. So all we're going to do, we're going to pick, which sets we want to union the finite collection. So we'll say let A1, A2, all the way, let's say AN be elements of our sigma algebra. Okay, and so I want to show that the union of these elements is an element of the sigma algebra. What I'm going to do is I'm going to define a countable collection. Okay, so we'll say Bn for n a natural number, right? The naturals are 1, 2, 3, etc. going off. We'll define this as follows. Actually, I should use a different index, not n. Let me use k. Bk for k, a natural number. We'll say that the first n elements of this sequence are precisely a1, a2, all the way to an. So I'm going to write that as bk is equal to ak for 1 less than k less than or equal to n. Okay, and then after that, the additional elements of this collection for k greater than n. So for k greater than n, I'm just going to say that bk is equal to the empty set. Now you can probably see what's going to happen so this is a countable collection of measurable sets, right? So clearly bk, right, this is a countable collection of measurable sets. Therefore, right, using that property of sigma algebras that we know, therefore the union, the countable union, this is a quick way of writing from, let me again be consistent, writing k is an element of the naturals. Sorry, I want to make sure this is clear for you to see. Therefore, the countable union here is a measurable set. It's an element of the sigma algebra. If you can see that as an element. Okay. Well, how do we go from this to a finite union? All we have to notice, and I'll just use a different color. We'll go up here. Notice that this union is actually finite. Why? Because if I write it out, right, this is equal to A1 union A2 union all the way to AN, right? Because the first n elements of this sequence are precisely the elements of this finite sequence here, A1, A2, all the way to AN. And then after that, after AN, I'm just unioning with the empty set. And I just keep doing that. Okay, well, this doesn't matter, right? Because if I union a set with the empty set, I get that set. So this whole business right here is actually just equal to the finite union, A1, A2, union, AN. Okay, and I can just also write that just for fun as a union from k is equal to 1 to n of ak. Okay, and we know that because this countable union is an element of our sigma algebra, then this must be. And again, I can also say, right, I say this is an element of our sigma algebra. The shorthand we've learned today is just saying this is a measurable set. And I'll try to transition to using that terminology more so you get used to it. Okay, so we found out that this finite union is a measurable set. And this completes the proof because this was just any old finite sequence in our sigma algebra. Okay, moving on. Now this is our the second part of the theorem, which is closure of our sigma algebras under finite or countable intersections. Okay, so what I'll do is I'll go ahead and we'll discuss the countable case first, and then drop down and prove the finite case. Okay, so we'll start with the countable case. Okay, so we start with a countable collection of measurable sets. We're going to say we'll say AN for n a natural number be a sequence of measurable sets. Okay, now I want to show that, let's say I want to show, which I can abbreviate WTS, that the intersection of all of these elements in the sequence is measurable, excuse me. Okay, now how am I going to do that? I'm going to recall, there's a really useful law in set theory you've probably heard about, recall De Morgan's law. Which basically says that if I can take, you can write it in two forms, the union, okay, and it doesn't matter, this can be countable, finite, whatever, okay, the union of any collection, we'll just say AN, you know, this can be indexed whatever you want it here, okay, but just focus on what's going to happen. If I take the union of some collection of sets and I complement it, what happens is the complement switches the union to an intersection, and then I complement each set in the intersection. So this becomes the intersection of AN complement. Okay. So this is one way to write it. The other way to write it, right, I can also say the intersection here, complement, is equal to the union of A and complement. So two of the De Morgan's laws. What I want to do, okay, so the goal for this here is we're going to use two facts from the sigma algebra. One is closure under countable unions, okay, and then closure under complementation, right? Okay, so here's a little hint. We know that this right here, this guy right here, okay, this is a countable sequence, so we know that this right here is an element of our sigma algebra, the union of the ANs. And because this is measurable, its complement is measurable. That's the second property of sigma algebras, being closure under complementation. Okay, and then we're going to get the intersection of AN complement. But the problem is we want the intersection of the ANs. We don't want this complement business. Okay, but recall, like for any set A, we can know that if we take the complement twice, like A complement, that's just A. Okay, so what I'm actually going to do in proving this, so let me start over here. I'm going to note that if I take, you know, we start with this sequence of measurable sets. I'm going to consider the sequence of the complements of each of these sets. So note that this sequence, this is a sequence in our sigma algebra. Okay, so these are all measurable sets, right? Because sigma algebras are closed under complementation. Okay, now therefore, this union here, so union for n and n, and in the naturals, A and complement is an element of sigma, okay, right? And that comes from the closure of sigma algebras under countable unions. Okay, now I'm going to apply De Morgan's laws. I know that because this is a measurable set, the complement of this guy, this entire thing, is also going to be a measurable set, okay? Then the complement of this guy is also an element of sigma, but the complement of this, if we look at De Morgan's law, is going to be an intersection. So when I compute this complement from the outside, what I get is that the intersection, so these are equal, this is equal to the intersection n and n, A and complement, and remember, we already have a complement in here, so we're taking this double complement. We know that this is an element of sigma, okay? But this, like I just said, we have this double complement, it'll cancel out. That's actually just the intersection over the naturals of AN, and that is an element of sigma. And that proves the countable case, which is the closure of sigma algebras under countable intersection. So we're done with that. Now for the finite case, it's easy. We're going to exploit the fact we just proved the countable case. Finite case. Okay, and it's going to look very similar to what we did for unions. So I'm going to pick our finite collection of measurable sets. Okay, and then I'm going to define a countable sequence, BK, indexed by the naturals, as follows, in a almost identical manner. Okay, we just make one change. So the first, just like before, the first n elements of this sequence will be precisely the elements of this finite collection we've selected. Okay, so bk is equal to ak for k between 1 and n. And then for n beyond k, what we're going to do, instead of saying it's going to be the empty set, we're going to just pick some element of this finite sequence. So I'll just say bk is equal to a1 for n greater than k. All right. So we know that from what we literally just proved, that the intersection over the naturals, I should say k, right? Yeah. Of bk, we already know that this is an element of the sigma algebra because we just proved closure under countable unions. Now, all we're going to do is write that out. So I'll just say, but this intersection, and then that's just equal to, we'll say a1 intersection a2 intersection all the way to an, and then after an, we just start intersecting a1. You know, we just keep intersecting a1, blah, blah, blah. Okay. Once you've intersected a1 once, it doesn't matter if you keep intersecting it anymore. Okay, so again, it doesn't make any difference how many a1s we've written here in the intersection. Once I've written intersection with a1 the first time, after that we're just done. So this is actually just the finite intersection. Okay, which again, just to write it explicitly, this is the intersection, that's a union. This is the intersection from k is equal to 1 to n of ak, and we've proven that that is a measurable set. And so now we have achieved the property of closure under finite intersections as well as countable intersections. Okay, moving on to our third property. To prove this one, we need to recall what it means for a measure, mu, to be a measure. What are those axioms? If you recall, actually I'll just write them here. Mu is a measure if there exists some a in our sigma algebra sigma, such that the measure of a is less than infinity. Recall that measures can map to infinity. And then our second condition was the countable additivity. Okay, so that's 1, and then number 2, actually I'll just say it like this. This is 1, and this is 2. If an, indexed by the naturals, is a pairwise, I'll just abbreviate that PW, pairwise disjoint collection of measurable sets, then if I want to take the measure of the union of an, I'll skip writing the indices just for time. I can, actually I won't. I'll just say from n is equal to 1 to infinity. I can write that as the sum from n is equal to 1 to infinity of the measure of each of the constituent sets. Okay, so that's what it means for mu to be a measure. Okay, we're going to use these properties. Specifically, we're going to start with this first one here. And since we know that there must exist for mu to be a measure, some measurable set with finite measure, we'll say let A be that set. So let A be an element of sigma such that mu of A is less than infinity. This is guaranteed because A is a measure, okay? And so I'm going to consider the following sequence, which is going to be given like this. We'll start with A, then we'll go to empty set. We just have A, and then the rest of the elements of the sequence are the empty set. Okay, going off to infinity. And we know that this is a sequence in our sigma algebra precisely because we know A is an element of our sigma algebra, and the empty set, by definition, is an element of our sigma algebra. Okay, so we have this countable sequence in our sigma algebra. Moreover, this is actually a pairwise disjoint sequence. Okay, and remember, two sets are disjoint if their intersection is empty. Well, if I take any two elements of the sequence here, if I take A intersect empty set, well, we know that's empty. And then if I take any two empty sets and I take the intersection of them, that's empty, trivially. Okay, so this is actually a pairwise disjoint sequence in sigma. So what we're going to do is we will apply the second property and note that the measure of A union empty set, I'll keep going all the way, this is going to be equal to the sum of the measures of each of these guys. So the sum from, I'll just write it like this. You know, we can just say, let's say this is B1, B2, B3, and so on. That's how we're going to define a sequence Bn, okay? Well, this is going to be the sum from n equals 1 to infinity of the measure of Bn, okay? What I'm going to do with this is I'm going to pull out the first one. So I will write it as this is equal to the measure of mu of B1 plus the sum from n equals 2 to infinity, because we pulled out the first element, the measure of Bn. Okay. And then that's right there, that's just the measure of A, plus we have this sum of the measures of the empty set. So, you know, actually I guess I just write it like this. Right. Okay. We have all these empty sets here. Okay. Now, this right here, okay, when evaluating this, go back to this guy at the beginning. When I take A union empty set union, continuing unioning with empty sets, I get A. So this right here itself is equal to the measure of A. So I follow this chain of equalities, and I get that the measure of A is equal to this. Well, if I subtract mu of A from both sides, right, I'm going to get that this whole sum right here, from 2 to infinity, the measure of the empty set is equal to 0. Okay. This is a sum of non-negative numbers, and we're saying that the sum of non-negative numbers, and these are all the same. Okay, we're just taking mu empty set plus mu empty set plus mu empty set, all the same. We're saying that the sum of these non-negative numbers are 0. The only way this can happen is if each of the elements of this sum are 0. So this implies that the measure of the empty set is equal to 0, and that completes the proof. Okay, finally we're on our last property for this theorem, which is that of monotonicity of measures. So if A and B are measurable sets, and A is a subset of B, we want to show that the measure of A is actually less than or equal to the measure of B. Okay, well this is actually quite easy. We just need to recall some set theory. Okay, I'm going to start on the right-hand side, and then I want to build a chain of inequalities that will show that the measure of B is greater than or equal to the measure of A. So I'm going to put mu of B here. Now, let's look at the situation A is a subset of B. Go back to set theory and remember the pictures we used to draw. Okay, what I have here, well, that's going to bother some people that the top is not perfectly flat, but that's okay. If this is B, and I have, what's a nice complement here? And this is A. Okay. I can actually write B as two parts. I can write B as the union of all the elements of B that are not in A. Actually, let me use a different color for that. So like in pink. So in pink, these are elements of B that are not in A, and particularly that is B minus A. Okay, and this is equal to, by the way, B intersect A complement by what we have just proven before. This is an element of my sigma algebra. Okay, just something to note. Okay, it's the union of what's in pink plus what's in A. And also note that A, I can write A as B intersect A, right? Because everything that A and B have in common is A, because A is a subset of B. Okay, so I can actually write this as the measure of everything that's in B and not in A. Actually, I'll need to use some brackets here. Everything that is in B that is not in A, union with we'll say A intersection B, like this. Okay. Now these are disjoint sets. You can obviously tell by the picture, right? I mean, everything that's in B but not in A would obviously not be in the intersection, right? So these two sets are disjoint. And then now we're going to exploit the property of countable additivity for the measure. Now, what I didn't prove was that countable additivity actually implies finite additivity. So even though this is a finite union, I can still distribute the measure over it. Now, how you prove that, it's similar to how we proved closure under countable unions for sigma algebras, okay? So you start with countable additivity. You get a sequence of finite sequence of sets that you want, okay? And then you how do you say that? Extend that sequence just adding on the empty set countably infinitely many times. You apply the definition of countable additivity, and then you recall that the measure of the empty set is 0. Okay, so you end up getting a finite sum. Okay, but anyway, we're just going to take finite additivity for granted in this proof for the sake of time. This is equal to the measure of B minus A plus the measure of A intersection B. And this is, I'll just write it here, finite additivity that we're using. Okay? Now, with this, we have the sum. This is going to sound kind of ridiculous, but we have the sum of two positive numbers, or two non-negative numbers. If I just take away one of them, I say ridiculous because it's obvious. If I just take away one of them, I'm going to get a smaller number. This guy I don't want to work with, so I'm just going to say that, well, obviously this would be greater than the measure of A intersection B, right? That's a smaller number because we took away this guy, okay? Well, the measure of A intersection B, right, because A is a subset of B, this is actually just A, the measure of A. So this is equal to the measure of A. And you apply this chain of inequalities. We have the measure of B is equal to the measure of this union, which is equal to this sum, which is greater than this guy, which is equal to this guy. So we have that the measure of B is actually greater than or equal to the measure of A. And that completes the proof. Okay, this concludes this video. When we come back, we're going to start discussing the Lebesgue outer measure. Thank you.